Thanks, Nathan. Good evening, everyone, or good morning if you, like me, are in California. So let's talk about self-driving. So as you already did, I want to take a few seconds to introduce myself. I grew up in France, moved to San Francisco 20 years ago. And so over the last 20 years, I had the chance to work in Silicon Valley, from startups to bigger companies. And I spent the last 10 years at Google/Alphabet. So as you pointed out, I first worked on deploying the first deep learning-based computer vision systems on top of Street View, part of the Street View team, to build Google Maps. And spent the last 3.5 years at Waymo, which is an Alphabet company working on self-driving cars, leading the perception and machine learning infrastructure teams. So recently, a few months ago, I joined Lyft, and more specifically, Lyft Level 5, which is the group focusing on building self-driving tech. So since I've been working on understanding the physical world all the way back from my Google Maps days. I've been truly amazed by the speed and scale of urbanization. Couple data points. It's estimated that 2007, so 13 years ago, was the year that for the first time more people in the world lived in urban areas as opposed to rural ones. By 2050, it is projected that 2/3 of the population, the world population, is going to live in urban areas. That's 7 billion people. And even if those projections predate COVID-19, I think it's pretty clear that that's a pretty massive shift toward urbanization, and that shift is going to keep its pace. So why are cities so attractive? I think it has to do with density. And thanks to their density, cities provide easy access to goods, services, people, jobs. But that density also deeply changes many of our habits and needs. And obviously, one of those big needs is around mobility. So unfortunately, the picture I'm showing here is kind of quite too common for many of us. And the rate of urbanization and density is actually creating a major challenge for mobility and modes of transportation. So it's pretty clear that adding more cars and roads to accommodate that growth will simply not work. And that's not a 10-year from now problem. That's something that's already very real today. When I first saw those numbers, I was actually pretty amazed. So 3/4 of US commuters today drive to work alone. Our current way is really not efficient. In terms of density and space utilization, 14% of Los Angeles is used for parking lots, is now parking, which is a massive number. In terms of public health, 37,000 people in the US die from vehicle accidents every year. On top of that, you can add another 58,000 people dying from vehicle emissions. Those are pretty big numbers. And that's fundamentally Lyft's mission, is to improve people's lives with the world's best transportation. So building the best transportation service is a very high bar. It's a very high bar because you need to have a lot of the parameters right. You need to be able to remove many barriers of adoption for that solution to be efficient. Affordability is definitely a big one. So even if today the cost of mobility is kind of hidden in car ownership, when you look at dollar numbers, it's a pretty big piece, big fraction of everyone's budget. Experience, obviously, using someone else's car from ride to ride is something to be managed. Availability, the bar here obviously is if via an app you can have access to a car faster than it would take you to walk to where you would have parked, you know that you have a good solution. So availability is key. Convenience, which is about having access to the right mode of transportation when you need it, whether it's a bike, a car, or public transit. Reliability and efficiency, obviously. Efficiency, sustainability are key to make transportation more integrated and scalable as we see more urbanization, and safety, obviously. So that's Lyft's approach to solve the transportation challenge, is to provide a bundle of services and implementing the idea that you should have access to the best mode of transportation when you actually need it at the time that's right for you via the same app. So beyond rideshare in the US, Lyft has also been growing a network of bikes and scooters that are directly accessible from the app. Lyft is also working very hard to connect you to public transit and existing transit solutions, and more recently has been working into getting into the car rental business. So numbers we see from the platform. So even again, if those numbers predate COVID-19, but those numbers tell us that it's working. So half of Lyft users today already use public transport, public transit at least once a week. So you can see that use of different modes of transportation. The scooter and Lyft network and bike networks have been growing nicely. Lyft is already the largest bike share operator in North America. And that, again, that multimodal approach to the problem is working. 20% of Lyft rideshare users have used bikes or scooters in their experience. So the talk was about self-driving. Why is self-driving important to transport as a service and to a company like Lyft? Because if you remember the major attributes we talked about, it just happens that autonomous vehicles actually provide a fantastic solution to many of them. Affordability, especially over time, as we can decrease the cost of self-driving cars, is going to be a key attribute. Experience, you can come up with a more homogeneous fleet of cars, and obviously the absence of a driver can be useful in some situations. Availability, and the availability point here is key. If you think about what it takes to outsource a couple hours of your driving to someone else every day, if you just do very simple math, you would come up with the conclusion that you would need a pretty staggering ratio of us having to become drivers for the driver supply to be big enough to accommodate for all those hours. And so actually, driverless technology is going to be a way to increase driver supply. It's very unlikely, actually, that it's quite unlikely that self-driving is going to decrease driver demand, but it's more likely that it will actually allow transport as a service to move from a couple percent penetration solution to a tens of percent market penetration kind of solution. Reliability, obviously, is a key attribute that self-driving cars can provide, and safety is another big one. So where is Lyft on its self-driving journey? So Lyft is going after self-driving with two major initiatives. The first one is around open platform. An open platform is a way for existing self-driving companies to make their self-driving cars available to the Lyft network and provide rides. So current deployments include Aptiv making its cars available to the Lyft network in the Las Vegas, Nevada area, and Waymo making its vehicles available in the Chandler, Arizona area. So that network is growing, open platform is growing. More than 100,000 rides, autonomous rides, have already been provided, which makes it one of the largest autonomous ride provider in the US. And the quality of those rides has been very good. Not only very good in terms of a star rating, but also very good in terms of experience, to the point where we can measure that people will be happy to ride autonomous cars again. The second big initiative that Lyft is putting together to after self-driving tech is the Level 5 group. So Level 5's core ambition is to develop a fully Lyft-owned self-driving tech stack. So the team has already been developing multiple generations of driverless capable cars, and is working on the software solution, bundling hardware and software to come up with a full package. So we're already currently testing autonomous rides with a safety driver in the Palo Alto, California area. So you should tell me, it's 2020. It seems that AV was supposed to be widely available by now. What is going on with the self-driving promise? So I'd like to spend a couple times giving you my perspective on that specific question, and also try and show you why Lyft has unique assets that have a great potential to change the game. For the longest of times, AV technology has mostly been associated with what we call perception. We've all seen those pictures of trucks, pedestrians, cars, cyclists, traffic lights being properly labeled on imagery and properly tracked over time. We've also heard many debates around sensors, cameras, radars, lasers, which are all instrumental pieces into building a solid perception stack. So a lot of the discussion has been evolving around perception when it comes to self-driving cars, and a lot of the perception technology at the end of the day has relied or is relying on machine learning and computer vision related approaches. And the last decade, it just happens that the last decade has been a golden decade for computer vision. Obviously, we heard a lot about deep learning today, whether it's about converging models or having the compute infrastructure, but deep learning approaches had a massive impact in that field, stating the obvious. And there are quite a few reasons why that happened in the last 10 years and not earlier. The first one I'd like to highlight is around data. Having access to large and high quality data sets has been key. And actually, we can see that in a very high level timeline I put together, that data sets have often been precursors to measure improvements. The first one, obviously, is ImageNet back in 2010 that really moved the classification problem forward. Another one is the COCO dataset released in 2015 that has been instrumental for detection and segmentation kinds of problems. One point I put in there is around multi-digit number recognition from street view imagery, because that's a piece I directly worked on. And as an anecdote, the first street number classifier that we were able to put in place required 2 billion samples with a B, 2 billion samples to train and converge, which is a huge number. Which takes me to my second point. As we've seen a couple of talks ago, there is a race between capacity in those networks. So you need, in order for a solution to learn a complex task, it needs to have access to enough parameters. And generally speaking, the more complex the task, the more parameters you're going to need in your solution so that the knowledge can be transferred. At the same time, if you just randomly pile more neurons into an existing net, it's pretty unlikely, or it's going to be very hard to make that network converge or make that network learn the task you're trying to pick up. So and in any case, the more parameters you have, the more data you're going to need, the bigger the data sets should be. Actually, what we should see across the progression in the complexity of problems that have been addressed in the computer vision space over the last 10 years, from classification to detection to segmentation. One of the reasons why that has been successful is because we've been able to work a subtle equilibrium between learning capacity, which has to do with how many parameters we can put, with network architectures and fundamentally, which are fundamentally hard-coded regularization that we put hard-coded in a network to try and simplify the task of learning, and data sets. Right? So working on those legs is what allows us to do better and better. So all that progress and all that success actually is what created a lot of enthusiasm and optimism in the self-driving space. But a self-driving system to work needs to handle human interactions, needs to make decisions. It also needs to adapt to changing conditions. And there's a whole decision-making or what we call planning problem that you also need to solve. And I think it's fair to say that the complexity of planning has been so far underestimated. It's very complex, and it has taken a little more time to solve than we would have expected. So let me briefly go through a very simple example to try and show why. So we talked about decision making. One of the ways you can model how you make decisions is by reasoning about who occupies space on the self-driving lanes. So let's start with a very simple example. So we drive the pink car. So the pink car is the car in control, and the gray cars are going to be other agents. Simple case, we just follow a car on a single lane. It's pretty clear. The space in front of the gray car is owned by the gray car. We just try and need to predict when the gray car is going to brake and keep a safe distance behind it. A little more complicated is lane merging example. So here, the location where the interaction is going to happen is known. That's where the two lanes are going to merge. But the timing is a little more complicated. Thankfully, there are some priority rules. So if you assume that the pink car has priority on the lane, then when given a choice, the pink car should be owning that lane. But you need to come up with rules and prediction models that will allow you to solve the timing problem. Right? Should you go before or should you go after the gray car? Even more complicated is a more general lane change. So not only you have the timing problem we just talked about, but the location where the interaction is going to happen is not even known because the two cars are moving, and where the lane change is going to happen becomes a challenge. So you need to come up with yet another set of rules and another set of logic that's going to be able to account for that. And since that location is moving, you actually need to grow awareness into your whole surrounding. So that's what's represented by those red strips. You need to have an understanding of what's happening in that whole space to make your decision. For instance, if you have traffic lights at the end of a lane, that whether they're red or green, it's going to impact the decision you should be making. If there's a crosswalk with a pedestrian that's crossing or about to cross the street, obviously that should impact the decision you're going to make. And very quickly, you can see that as you add more complex situations, more agents. So here, another car or a motorcycle cutting lanes behind you. The more agents you add, very quickly the set of rules and logic you need to put it together to make it work grows exponentially. And that's kind of the complex development loop that we've been going through when it comes to planning in recent years. Is complexify the set of rules, drive, see problems, what we call disengage. So safety drivers telling you, hey, that behavior was not optimum, fix the rules and go back in the loop again. And that has been a very slow converging process along the way. Another problem that we face here is the capacity problem. If you only come up with a set of rules that you program, you're only going to have access to so many parameters. And even if the task of driving is obviously not general AI, it's complex enough that you need to have a lot of parameters for the system to learn all the knowledge it's gonna need to learn to succeed. So that's why recently approaches have been trying to mix machine learning and expert rules. Expert rules are very useful to set boundaries and safety boundaries on the problem. Machine learning is very useful to give you capacity. And as we discussed, capacity is a function of size. And the more parameters you have, the more data you're going to need. And so the need for data to make your solutions converge is key, and a very large volume of data. So that's thanks to its ride-sharing service, Lyft has access to a lot of miles, a lot of driven miles every day. And so we've been embarking on a journey to accelerate autonomous driving with the utilization of the use of that ride-sharing data. So how much data do you need? It's very hard to say, but all we know is that extreme driving events, such as fatalities or injuries, happen very rarely. So fatalities are every 100 million miles, injuries every 1 million miles. So it's very hard to predict, but to develop a full driverless program is probably quite conservative to bet on 100 million miles. Maybe 1 billion is closer to what you would need. it's hard to say, but fundamentally those are very big numbers. And so that's why we started to equip a subset of cars on Lyft's network with low-cost camera sensors that we use to capture scenarios drivers face daily. So actually this week, we published a blog post on the topic. I invite you to go and get more details on medium.com/Lyft Level 5, which is our official blog. So we already achieved quite a bit of success. So here you can see how we've been able to reconstruct a geometric map of San Francisco, only using those lower cost cameras deployed on the Lyft fleet. Again, those maps are built, geometric maps are built with no human work, no human intervention. On top of geometry, you can also come up with a semantic understanding. So here it's an example of lane mapping. So being able to map lanes and how those lanes are used, part of traffic patterns. And that learning is based on actual trajectories and driving from actual humans. An example of the usefulness of that would be to learn trajectories. So if, since we have enough samples of how humans naturally drove intersections, for instance, that we can learn from that knowledge and put it into the behavior of our self-driving cars. The big piece on the cake is to, beyond that static map and static understanding of the intersections or scenes, is to put dynamic agents. So there are two big challenges there. The first one is to understand the trajectory of ego, so the car you're driving, and even more complicated, mapping trajectories and behaviors of third-party agents. So here you can see how we succeed to do that with cheaper cameras. And when you actually combine all that data, so static map plus all dynamic agents, you actually come up with a with a scene you can use to train your planning algorithms. And doing that at scale, you actually come up with a very large collection of scenarios that not only can be used for your planning training your planner, but also doing validation at scale and convincing yourself that your system is ready to go. So we talked at length about how having access to data is key and has been precursor to many improvements. And so I have a special gift for you today. One of the problems we didn't talk a lot about is the prediction problem. So we saw how handling human interactions with our drivers and how decision-making are complex and active problems, challenges still open. And one of the key ingredients to make it work is to be able to understand agents around the car and be able to predict their future behaviors. That's what we call the prediction problem. And so we just announced, and we are just making available what we call the Level 5's open prediction dataset, which we believe is the largest and most complete data set available out there for prediction, for the prediction problem. So it contains logs of over 1,000 hours of traffic agent movement. So that's 170,000 scenes that are roughly 25 seconds long. To build that data set, we required 16,000 miles of data collected from our AV fleet. And what's pretty unique about it is that it also includes HD semantic maps that contain more than 15,000 annotations. That's a lot of prior knowledge of the scenes we've been driving, as well as aerial views of the areas. And we believe that those two components are going to be key in solving the prediction challenge. So you can download it today. We're going to kick off a competition in August on the Kaggle platform. So actually, it's more than data. There's a software kit. There's a website that you can access to have a high-level description, a viewer, and a link to download. There's also a blog post, again, on medium.com/Lyft-Level5. And last but not least, there is more of a scientific paper that goes into more details into what's in the dataset and the software kit. So in conclusion, we talked about how Lyft's mission is about providing the best multimodal transportation, how autonomous vehicles are a core component of that solution. We talked about how Lyft's Level 5 is developing a fully capable AV system on its own. We went through the challenges of dealing with people interactions and decision making and how it remains an open problem for AVs more broadly. We went through efforts that Lyft is doing into building a big enough data set using data coming from Lyft's ride-sharing network. And last but not least, we talked about a pretty big state-of-the-art open prediction data set that we are making available today and to help accelerate research in the space. Thank you.